Cold seas press against timber hulls as wind-driven waves tax joints, forcing builders to reconcile material limits with survival across the North Atlantic early medieval era. Unpredictable wave loads demanded hulls flex without catastrophic joint failure. Repeated bending cycles transformed rigid strength into liability during prolonged North Atlantic crossings under maritime conditions. That flexibility required overlapping planks to distribute stress, resisting failure. This approach treated the hull as a system absorbing energy rather than opposing it directly continuously. Overlapping planks increased seams, introducing leakage risks under sustained immersion. Water entry became expected behavior, shifting design priorities from prevention toward controlled tolerance over long voyages. Leakage risks forced sealing methods accommodating movement without brittle cracking. Seals had to compress, expand, and recover repeatedly as planks slid microscopically with waves beneath hulls. This need elevated tarred wool and iron rivets, importance structural. Organic fibers and malleable metal worked together to maintain pressure despite constant deformation from sea motion. Rivets concentrated loads, so spacing balanced strength against added weight. Too many fasteners stiffened planks excessively, while too few allowed joint separation during heavy seas offshore. Added weight reduced speed, threatening evasion and cargo capacity simultaneously. Speed determined survival by limiting exposure, time to storms, and hostile encounters across open water routes. Speed losses encouraged long, narrow hulls, minimizing drag through water. Length increased hull speed potential without proportionally increasing displacement or material requirements beyond local resources available. Narrow hulls compromised stability, demanding low centers of mass aboard. Crew placement and cargo arrangement became critical to prevent excessive rolling during cross-sea travel periods. Ballast stones provided mass while remaining adjustable for voyages seasonally. Loose ballast allowed redistribution responding to changing loads and sea conditions encountered throughout extended coastal journeys. Adjustability mattered because cargo, crew, and provisions varied constantly aboard. Even small differences in weight distribution altered how the hull met waves during long passages offshore. Variable loads altered trim, affecting steering and wave response predictability. Trim influenced rudder effectiveness and the angle hulls presented to oncoming seas under shifting wind patterns. Steering challenges led to side rudders exploiting water flow leverage. Positioned laterally, rudders generated control without requiring deep keels that would hinder shallow landings along coasts. Side rudders freed stern structure from complex underwater penetrations maintenance. Fewer openings below the waterline reduced persistent leakage risks and simplified emergency repairs during remote voyages. Reduced penetrations limited leaks, simplifying repairs during coastal landings frequently. Crews could address damage using shore access rather than dry docks unavailable in early medieval Scandinavia. Frequent landings shaped shallow drafts, allowing beaching without damage repeatedly. Shallow drafts reduced grounding forces when hulls contacted sand or gravel during routine coastal travel cycles. Shallow drafts constrained keel depth, reducing directional stability offshore significantly. Limited keels allowed sideways drift, requiring constant corrective steering effort under sustained wind pressure at sea. Reduced stability required sail plans, balancing force and control carefully. Sail area and shape determined how power entered the hull, without overwhelming stability margins during gusts. Square sails delivered power, but amplified heeling under gusts suddenly. Sudden lateral force shifted center of pressure faster than crews could react aboard lightly loaded vessels. Heeling risk limited mast height relative to hull stiffness available. Shorter masts reduced leverage applied to the hull during wind surges encountered across exposed northern seas. Hull stiffness depended on timber selection and grain orientation precision. Straight grain resisted splitting, while curved growth matched hull shapes formed under sustained bending stress cycles. Timber choices reflected forests, transport costs, and seasonal cutting windows. Builders worked within what landscapes allowed, rather than idealized specifications, defined by distant theoretical design principles. Seasonal cutting reduced moisture, improving strength and reducing rot formation. Lower moisture content limited fungal growth once planks entered service within damp marine environments persistently encountered. Rot threatened planks, necessitating ventilation and drying between voyages ashore. Drying interrupted biological decay cycles, otherwise accelerated by trapped moisture inside tightly built wooden hulls. Continuously, drying cycles influenced storage sheds and inverted hull practices locally. Turning hulls allowed gravity and airflow to remove residual water from seams inaccessible during a float operation. Storage constraints limited ship size to manageable communal labor resources. Large hulls exceeded capacity for hauling, repair, and protection ashore within small dispersed coastal communities seasonally. Labor limits encouraged modular repairs using standardized plank dimensions patterns. Standard sizes allowed damaged sections replaced without reshaping entire hulls during short maintenance windows between voyages. Standardization simplified replacement but constrained hull curvature extremes under load. Builders avoided aggressive shapes that complicated plank interchangeability under stress from repeated wave impact cycles offshore. Curvature limits influenced wave piercing versus riding behaviors in seas. Hull shape determined whether energy passed through or lifted vessels upward when encountering long ocean swells. Riding waves reduced slamming, preserving joints and crew endurance long-term. Reduced vertical acceleration lessened structural fatigue and human exhaustion across repeated crossings of exposed northern waters. Crew endurance depended on shelter from spray and wind exposure. Continuous wetting accelerated heat loss through convection and evaporation, affecting alertness, strength, and decision-making capacity. Minimal decking balanced protection against added weight aloft during storms. Partial decks shielded crews while preserving low centers of gravity, essential for stability in narrow hulls. Weight aloft worsened roll periods, increasing fatigue and risk aboard. Longer roll cycles exhausted crews and strained rigging attachments during extended exposure to irregular wave patterns. Risk management favored experienced crews, understanding sail reduction timing intuitively. During sudden squalls where delayed reactions translated directly into capsize risk under narrow hull conditions offshore. Sail reduction required rigging accessible under motion and darkness conditions. Because crews worked barefoot amid rolling decks, where hesitation increased strain on hull and mast systems. Accessible rigging shaped mast placement and deck layout under constraints, imposed by balance, visibility reach, and structural continuity during heavy seas, when movement was unpredictable aboard. Deck layout limited storage, forcing compact provisions and tools choices. That maximized caloric density durability and multi-purpose use within restricted volume, exposed to moisture constantly aboard. Compact storage influenced voyage duration and coastal navigation strategies, preferences, favoring shorter hops between landfalls, where resupply and drying reduced cumulative risk from prolonged exposure offshore. Coastal navigation reduced exposure, but demanded frequent landfalls for safety, increasing abrasion cycles on hull edges and reinforcing design emphasis on shallow draft durability over seasons. Frequent landfalls reinforced shallow draft and robust hull edges designs. Because repeated grounding loads punished fragile forms and rewarded structures, tolerating impact without catastrophic splitting failure. Hull edges absorbed impacts, requiring sacrificial elements replaceable after damage. So primary structure remained intact, while outer components were repaired ashore using limited tools and time. Replaceability reduced downtime, but increased maintenance labor over each season, shifting costs from catastrophic loss toward predictable communal work distributed across crews during calmer months annually. Seasonal maintenance aligned with agricultural calendars and weather windows locally. Because ship labor competed with harvests, requiring coordination of manpower within small communities facing limited margins. Weather windows dictated launch timing and fleet coordination across regions, ensuring vessels departed together, reducing isolation risk and enabling mutual support when storms disrupted navigation unexpectedly. Fleet coordination standardized designs, enabling shared knowledge and repairs between crews who recognized proportions, materials, and failure modes, regardless of origin or builder tradition, regionally spread. Shared knowledge stabilized performance expectations under uncertain seas over voyages, allowing planners to estimate risk based on precedent rather than hope when committing people cargo resources. Predictable performance allowed planning routes balancing risk and reward carefully, by selecting passages matching vessel limits rather than forcing holes beyond tolerances during unfavorable seasons offshore. Route planning favored currents and prevailing winds, exploitation through experience, accumulated across generations, observing how water movement reduced effort and exposure when aligned correctly with hulls. Wind exploitation shaped sailcloth durability and weave density requirements aboard. Since repeated flapping degraded fibers faster than steady tension maintained under controlled loading during extended crossings. Durable sailcloth traded weight for longevity under ultraviolet exposure conditions, accepting reduced acceleration in exchange for predictable performance across seasons without frequent replacement, consuming scarce labor. Heavier sails required stronger yards, increasing weight aloft instability risks, which amplified rolling moments and demanded careful balance between propulsion and survivability during sudden squalls offshore. Yards needed flexibility to absorb gust loads without catastrophic failure, since rigid spars snapped abruptly, transferring shock into mast steps and hull structure fast under strain. Timber species choice, balanced stiffness, strength availability, and transport limitations. Because ideal woods often grew distant from coasts, where moving long spars imposed high energy costs. Long straight trees constrained harvesting locations and seasonal access routes, tying shipbuilding schedules to specific forests, reachable during frozen ground or dry summer paths only annually. Shipyards clustered near coasts to minimize timber handling stresses significantly, reducing overland transport damage while allowing immediate launch and testing under real marine conditions after assembly. Assembly near water reduced hull deformation before first launch events, since completed hulls unsupported over land sagged under their own weight, distorting plank alignment permanently otherwise. Initial launching imposed bending forces, revealing weaknesses immediately during construction. As hulls transitioned from supports to buoyancy, unevenly stressing joints and fasteners before crews ever sailed. Early failures provided feedback, shaping incremental improvements over generations' time, embedding lessons into practice rather than theory as builders adjusted proportions, materials, and methods conservatively thereafter. Design evolution favored gradual modification rather than radical, untested changes, because each vessel carried lives and resources, making failure unacceptable beyond narrow margins allowed by environment. High stakes discouraged experimentation beyond proven environmental tolerances repeatedly historically, reinforcing reliance on accumulated success rather than speculative efficiency when survival depended on predictability alone offshore. Knowledge transmission relied on apprenticeship, limiting deviation from tradition practices, ensuring techniques persisted through observation and repetition rather than written abstraction, unsuited to variable sea conditions. Lack of instruments required proportional rules remembered through repetition alone. Embedding measurement within bodily memory and visual judgment, formed by countless hulls, built and tested previously. Hull proportions encoded stability margins without mathematical formalization methods explicitly, allowing builders to reproduce safe forms intuitively while responding subtly to local conditions and materials available. Repeated construction, calibrated proportions against storm survival outcomes consistently observed, as each voyage tested assumptions and confirmed which balances endured when waves exceeded expectations season after. Open seas served as unforgiving testing environments for designs repeatedly, offering immediate consequences where weak decisions manifested as damage loss or forced retreat without second chances. Failure costs included lives limiting acceptable risk thresholds severely always, anchoring design decisions in survival rather than ambition within narrow margins imposed by cold, unpredictable seas. Redundancy appeared where possible, despite penalties and mass accumulation overall, because failure of single systems at sea carried consequences beyond repair capability during voyages offshore routinely. Oars provided auxiliary propulsion when wind direction became unfavorable, suddenly allowing crews to maintain control near coasts, harbors, and during calms where drifting increased exposure time. Oar ports weakened planking, demanding localized structural reinforcement measures. On board, because repeated rowing loads concentrated stress around openings already compromised by motion and water ingress forces. Moving oars required seals, tolerating motion and persistent leakage conditions, so materials compressed without tearing, while allowing shafts to pivot under load through waves continuously encountered. Rowing consumed metabolic energy, constraining crew endurance and size capacity. Because calories burned, moving hulls reduced reserves needed for warmth, alertness, and labor after landfalls ashore. Hull length scaled with available manpower and resistance considerations combined, ensuring oar spacing matched rower strength, while displacement remained manageable under sail and load variations encountered. Ship size reflected social ability to provision crews, sustainably over time, revealing organizational capacity to feed house and replace sailors across seasons without collapse or abandonment. Food storage faced spoilage accelerated by moisture and temperature fluctuations, forcing reliance on dried, smoked, or fermented supplies tolerant of damp holds during extended passages northward. Ventilation reduced spoilage, but admitted spray increasing dampness on board, continuously requiring careful balance between airflow preserving food and excess moisture, degrading wood rope and clothing stores. Moisture control traded thermal comfort for material preservation priorities, consistently as crews accepted cold airflow to slow rot mold and corrosion-threatening holes, rigging, and provisions. Clothing compensated for exposure, not mitigated by hull design alone, making garments integral survival systems, managing heat loss, where ships offered minimal shelter from wind spray. Wool insulation retained warmth despite saturation through trapped air pockets, allowing continued insulation even when soaked, unlike fibers, collapsing under water weight during constant spray exposure. Heat loss dominated by convection from constant wind exposure, aboard accelerating cooling rates beyond radiation or conduction effects whenever wet surfaces met moving air over decks. Reducing exposure time minimized cumulative heat loss risks significantly overall by shortening crossings and labor periods under wind, where physiological reserves declined faster than replenished on board. Speed shortened crossings, lowering probability of encountering storms mid-voyage unexpectedly, thereby reducing cumulative structural fatigue and human exhaustion across unpredictable weather windows common in northern seas. Smooth hull surfaces reduced drag, improving efficiency measurably during travel, allowing vessels to maintain speed under lower wind force and reduced rowing effort over distance traveled. Hull smoothness required regular scraping, increasing labor investment, demand seasonally as marine growth accumulated quickly in productive coastal waters, between voyages requiring communal maintenance periods ashore. Marine growth increased drag, penalizing long stationary periods afloat severely, encouraging frequent hauling or movement to prevent fouling from undermining speed and fuel efficiency measured in calories. Seasonal sailing limited growth, aligning maintenance with usage cycles. Naturally, since winter, storage interrupted biological accumulation, while summer voyages maximized travel before fouling imposed penalties again. Winter storage ashore prevented ice damage and biological accumulation effects, protecting hulls from crushing pressures, while allowing thorough drying impossible during frozen water conditions afloat seasonally. Ice pressures exceeded hull tolerances, necessitating avoidance strategies regionally enforced through route selection timing and cultural knowledge, preventing exposure to freeze-up zones beyond vessel capacity. Design constraints defined navigable ranges, excluding extreme polar waters deliberately, because sustained ice contact imposed loads. No wooden fastenings could absorb repeatedly without failure or abandonment. Expansion followed routes matching vessel capabilities precisely over time, repeatedly producing corridors of movement shaped by hull limits rather than ambition alone across generations of sailors. Exploration feedback refined construction choices through accumulated experience continually shared as observations of failure, success, and endurance circulated among builders, sailors, and communities over decades. Collectively, failed voyages informed caution, embedded within collective memory structures, culturally guiding decision-making through stories, practices, and taboos that constrained risk-taking beyond tolerable environmental limits. Ritual practices reinforced respect for environmental limits, pragmatically understood, communally embedding operational knowledge within ceremonies that synchronized effort, timing, and restraint with seasonal natural forces encountered. Longships functioned as integrated systems, combining materials, environment, humans continuously, where failure or success emerged from interactions rather than isolated components, acting independently under stress conditions. No single feature ensured survival, independent of others operating together, because imbalance anywhere transferred stress across systems until weakest links failed during adverse conditions offshore, inevitably. Balance between systems mattered more than peak performance metrics alone, ensuring ships endured variability rather than excelling briefly before succumbing to accumulated strain over repeated voyages. Longevity indicated successful alignment with persistent environmental forces over generations, demonstrating designs refined by survival rather than innovation, detached from lived maritime realities and constraints imposed. Similar designs spread where conditions mirrored original assumptions closely enough, allowing replication without major modification, as wave climate materials and social organization aligned across regions naturally. Different seas exposed weaknesses when assumptions no longer held true, forcing adaptation or abandonment where hulls met unfamiliar wave periods, winds, and loading regimes beyond experience. Later, technologies shifted constraints, changing optimal maritime solutions entirely thereafter, as metals, engines, and instruments redefined trade-offs between strength-speed control and endurance across oceans globally. Longships demonstrate survival through constraint management rather than dominance alone, illustrating how understanding limits enabled movement, trade, and exploration within hostile environments without overcoming them completely.